Alright class, in today's video we're going to explain electromagnetic induction. That's how electricity causes a magnetic field to be produced, and also moving magnetic field causes electricity to be used. This is very useful in many different applications like generators, transformers, electric guitars, and most of technology today is based on the concepts you're about to learn. This picture I actually got from the Hewitt-Druitt YouTube page. It's from Paul Hewitt, who wrote the conceptual physics textbook. I actually met him in a conference in San Antonio. Really interesting guy. Essentially what he says in his video, which is true, if you have a magnet and you move it over a circuit, you could actually induce or make a current. Okay? So by having the motion of the magnet makes electricity work. Another way it would work is if I actually move my wire, I could also induce a current because the wire is going with the magnet. So we learned that current carrying wires produce a magnetic field around them. The reverse is also true. A changing magnetic field can induce or create a current in a wire. Now, this current is called induced because it comes about by the changing magnetic field. The many different factors that cause induced current, the strength of the magnet, the direction, the speed of the magnet, and so on. Now you might remember the right-hand rule from the magnetism unit. In your right-hand rule, you take your right hand, your thumb will point towards the direction of the current. The direction that your fingers curl will be where your magnetic field is. So in this example, my thumb is pointing up. You would turn your fingers this way. So in the front of the page, the current will be going to the right. Behind the page, the magnetic field will be going towards the left. So based on that, if you hold a magnet near a coil of wire, nothing's going to happen. But if you move the magnet towards or away from the coil, a voltage and current is also induced. Depending on the direction of your magnet, you'll get an induced current. You notice that in this case the wires have to be coiled in order to get the right-hand rule to apply. So you could actually relate this to the right-hand rule with a magnet. Your thumb would be the direction of the magnet. The induced current will be the coil, or counterclockwise, just like how your fingers coil in your right hand. When the magnet moves towards the coil, the magnetic field through the coil will increase, inducing the current. If it's moved away, the field will decrease, creating a current, but also in the opposite direction. So in this example, bar magnet and ammeter, no current. As I move the magnet towards the current, or towards the coils, you'll induce a positive current. As I move away from the coils, this way, you're going to get a negative current. The changing magnetic field causes an induced current. Since the source of EMS, electromagnetic force or voltage, is needed to produce a current, remember Ohm's law, V equals I times R, a moving magnet acts like a source of the electromagnetic field. So we could say a moving magnet induces an EMF in the coil, producing the induced current. Remember, just like if you connect a battery to a circuit, you'll create a current out of it. Essentially, the magnetic field is inducing the voltage first, and that voltage creates the current. Another way to describe this is called magnetic flux. Flux is similar to luminous with light flux or electric flux. It deals with the magnetic field and a surface in which it passes. It's also a measurement of magnetism. The way to figure out your magnetic flux is the dot product, that means the angle matters, of your magnetic field and the area you're measuring the flux through. Now, how do we actually change the EMF and flux? One, the coil could spin, inducing bigger current. The coil could change in your area, make it bigger and smaller. That's how a generator works. The coil can move out of the electric field. The magnetic field could change strength if you have a stronger or weaker magnet. Since the flux depends on all those factors, any of them could change to produce an induced EMF or current. This is an example of Lenz's law. Moving a magnet through a coil, the EP fields, or magnetic flux, is increasing, so the flux also increases. The induced field must be opposite the direction of the original field because you're creating the induced current. Remember your right hand rule again, that's what creates the current of your fingers coiling around. Here's some applications of using electromagnetic induction. An electric generator transforms mechanical or moving energy into electrical energy. So it generates electricity. Here I have a north and south pole of a bar magnet. You're going to move this coil and rotate it around by mechanical means, usually a gas generator. If you had propane, they'll turn around, they'll actually induce a current, and then that creates a circuit which might light up a lamp. So if your electricity runs out, or say the wires got broken in a storm or something, you could use a generator to induce an electric current. As you can see here, the coil is spinning. Based on the right hand rule, you'll induce your current to make the electrons move. Electric guitars work the same way. In your guitar strings, it's actually magnetizable. There's the pickups in the electric guitar, which is essentially a small magnet. As you're playing, your magnet coils will actually go towards the right, and that's what actually creates the induced current. Final use for it is in transformers. Transformers are used in not movies, but actually movies too. Also in creating big electric circuits for powering a lot of homes. So let's say we have a power plant with electricity. We want to start with low voltage, but then we're going to use a step-up transformer that increases your voltage based on the induced current. That's why in the wires you're going to start with a high voltage, and then as the electricity is going across the wire, we want to step down the voltage at each part by essentially doing the opposite direction of your motion, and that's what creates low voltage that could power up your homes and businesses. So let's say I start with 1,000 volts. If I use 10 volts for this home, there will be 990 volts left to other customers, and it just keeps stepping down from there until you power up all your homes. Alright class, so that covers everything on induced current. Check out the Paul Hewitt video, Hewitt-Jewett Induction. It has a lot more information that's well received as well. If you have any questions, feel free to leave a comment down below.